Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 17 of 22. It is one thing for a model to draw a flat 2D graph of a molecule. It is an entirely different engineering nightmare to generate a stable 3D geometric cloud of atoms. You can have a generative model build a beautiful 3D point cloud of a drug that perfectly fills a target protein pocket, only to watch the whole thing fall apart in post-processing when the system fails to guess where the actual covalent bonds should go. The solution to this disconnect is bridging 2D and 3D generative spaces. In generative chemistry, data modalities dictate what your model can understand. The first modality is 2D topological space. Think of this as a standard molecular graph. Nodes represent atoms with specific types, and edges represent the chemical bonds connecting them. The model outputs an adjacency matrix telling you exactly what is connected to what. Graph neural networks handle this well. The problem is that molecules exist in the physical world, not on paper. A 2D graph gives you the binding topology, but it completely ignores the 3D geometric structure. Without spatial coordinates, you cannot accurately calculate quantum properties or perform structure-based drug design. To fix that, models shifted to generating molecules directly in 3D geometric space. Here, the output is a point cloud. The model defines the atom types and their exact x, y, and z positional coordinates. The technical hurdle here is maintaining SE3 equivariance, ensuring the molecule remains mathematically consistent regardless of how it is rotated or translated in space. Here is the key insight. Generating in pure 3D space means the model does not explicitly generate the chemical bonds. It just places atoms in space. You have to infer the binding topology afterward through post-processing algorithms. This introduces major errors. Returning to the drug pocket scenario, your model might arrange atoms in a shape that physically fits the target, but because it never considered binding topology during generation, the post-processing step might infer impossible covalent bonds. For larger molecules, directly generating a stable 3D structure without any topological guidance often results in a suboptimal solution. This brings us to generating in 2D and 3D joint space, which produces a complete molecular structure simultaneously. The model outputs the atom types, the discrete adjacency matrix for the bonds, and the continuous spatial coordinates all at once. By bridging these two spaces, the modalities constrain and correct each other during the generation process. The 2D topology acts as a blueprint, guiding the 3D structure to ensure the spatial arrangements are chemically feasible. At the same time, the 3D geometry refines the 2D graph by suggesting plausible bonding patterns based on spatial proximity. The main technical challenge in this joint approach is managing two fundamentally different data types. You're forcing the model to handle discrete topological structures like bond types alongside continuous geometric structures like coordinate values. Different architectures resolve this differently. A framework called Jodo treats both the topological and geometric structures as continuous variables to process them together. Another model, MuDis, handles them separately, applying a discrete process for the topology and a continuous process for the geometry. You cannot reliably generate novel, functional drugs by guessing the physical shape and hoping the chemical bonds work themselves out later. True molecular generation requires topological blueprinting and spatial positioning to interact and complement each other in the exact same computation. That's all for this one. Thanks for listening and keep building.